Hello everyone, and welcome to the next hour lecture. Last time we started the sensor chapter. Today we'll have the second part of the sensor chapter. We will have the signal conditioning. What is that and what is that about? So first of all, let's see how usually we sense the data or the physical environment around us. Usually let's say we are seeing something, we hearing, taste or touch or something like that, but we usually gather via our sensor organs, not devices, yeah, via our sensor organs, and transfer the information to our brain. And what is interesting there, that let's say we are hearing, we are listening for a class, and usually we have in a class many people. We have, let's say, hundreds of people, yeah. But somehow you can detect your colleague, but not a specific colleague, but the colleague that you want to hear, yeah. And you focus on him, let's say like this, and you understand him. But after you try to focus on another part of the class and you detect what he is saying, what is interesting, everything you detect from the big noise and different environment, let's say like this, yeah. So, and somehow our brain process this information. More than it, after that, we can repeat it or register it. So report the information in, let's say, kind of already conditioned information. So today we will speak about how to detect from the noisy signal, noisy source of signal, and to gather the information and to condition it in order to be able to process it, to show it, to transfer it to another systems, another component of the system. So in our case, we have here our organs, yeah, sensing organs. So we gather the information through our ears and transfer the information here, and in the brain we have the magic. For electrical system or IT system, let's say information technologies, we have some, not instead of organs, we have some devices or some components that are detecting physical changes from the physical environment, yeah, sense it, transduce, and after that we are providing some information. We are converting it into a measurable signal. So let's go further and to make some conventions, but not, first of all, let's remark again what we have to, what is the real information source. Usually we have source about the environmental temperature, humidity, sound or noises, and others, yeah, exactly how we discussed in the previous topic. Yeah, but this information, first of all, we should understand the nature of this and detect properly, and why we should understand the nature of the information source, because we need to know what are the issues that could be detected in this in the environment, in order to be able to extract the useful information from all the information that is around. So let's continue then. Now let's classify what is the what information means, because the meaning of the information should will give us understanding, common understanding, what it comes from and what for, or but let's say like this. First of all, information is, by the way, if you mind, please provide me some definitions about the information that you have until this moment, because okay, I have here something that is explained maybe, but before that, did you have any definition of the information in your courses or on your daily life, or I don't know, any sources? Yeah, because information, let's say it's something that with data with means, yeah. But first of all, let's see what is the source of the information, or when I want to transfer information, how we are transferring the information. And usually from the ancient period, we have some information like, okay, somewhere in Egypt we have something like this, yeah. Now let's say like this. And this was the information that it is something, and after that next is going to a tree and so on, and we form from those symbols, let's say like this, yeah, some sentences. And what's interesting that in the ancient symbols, every symbol was mentioning something, some things, yeah, and collecting these things, combining them, we are transferring the information. But somehow this is, let's say, a call, yeah, and nowadays, I don't know the whole history, but somehow we have some specific symbol. Let's say we have a call, yeah, call, W, and now this is a tree, yeah, and we selected 23 or 24 symbols that we can define everything with those symbols, and we name them, those symbols, letters or literal symbols, and we have X, Y, A, B, C, and so on, and with those symbols we can define or all the information we have around. More than it, between the symbols, we can have some literal symbols, yeah, 3, 5, yeah, and those are just some scratches, yeah, of the special symbols, special chars, yeah, nothing different between X and the 3. If we will look about the method how we scratch it on the table, yeah, but those Arabic literal symbols helps us to define the quantity. Yeah, another scratches, let's say like this, that we are able to define quantity. Okay, 3, 5, and when we are saying 35, we are saying something bigger than 7. Yeah, and we can even compare. Okay, 35 if 22, and we can say that okay, here we have more 42, and we already can measure some quantity. But by the way, most probably you heard about the movie about some people that are were looking for the answer for the main question. Please raise your hand who heard about this movie. When the people were building the biggest computer ever to answer to this question. In Russian will be Автостопом по галактике. Please, just raise your hand if you heard about that. And please give me the answer. Okay, give me the answer that responded this computer. What was the answer? You can say in voice, because as I detected the chat is a little delaying. But what is the answer for the most important question? Okay, and most probably we already have it, is 42. Yeah, and why 42? What is that 42? Is something that, okay, yeah. Thank you, Pavel. So It's 42, but what was the question? Okay, we don't have the question because we don't have the mean of the data. Why, what, how much, 4 and 2, and maybe we can even round it on to be 24 and something like that. Because without having a mean, we cannot understand what is that. And from the moment we put here, let's say 70 kilometers per hour, we start to feel the speed, yeah, because we understand that we are measuring or we are providing the quantity of the speed, yeah, or the 50 volts, okay, or let's say 25 Celsius degree. Okay, and let's imagine now I will say, but please concentrate on what I'm saying, but very much, yeah. Let's speak about the temperature, and what if I will say you minus 10 degrees. And sometimes when you are trying to feel the information, you will see that it's starting to be cold. Somehow imaginary, but you feel the cold around you. So that means when you are giving the mean of the data, it starts to be information. So the main definition, at least in our course or in our discussion with me, what I mean, information is data that has some meaning. Yeah. So when I saying just 2, I don't know what is that, but when I say 2 students, in this case, I see how many people I mean. Yeah, more than it. Let's say that we have 25 degree. Yeah, we have the 25 degree, but now is okay. At this moment is 25 degree. And I write down this information, and tomorrow I will say it's 25 degrees. It's not correct, because meanwhile something changes, yeah. And in order to keep tracking the information, we somehow looking to the, let's say, thermometer, to the sensor, say, okay, 25 degree, 25, 26, 20, 27, 29, and so on. So I start to track it, yeah, and I see that I'm connected to the source of the signal about the temperature. So in our case, in this case, we have a new definition of something, yeah, or definition of the signal. What is a signal? The signal is evolution of the information in time. So just some example. You call some friends, and you are hearing them, and at a certain moment you detect that nothing changes in my phone. Okay, oh, I don't have signal. Yeah, because the verbal information is not doesn't have evolution. No any words. Yeah, so I lost the signal. After that, I do something. Okay, I have the signal. Yeah, now the verbal or sound information started to continue in this case. So now we'll have many, let's say, levels of the information. First of all, we have some symbols, maybe some cows or trees, but in our case, we encode all the information by some literal symbols. In our case here, we have Latin literal symbols. Yeah, but in case we are using some numerical this is the first level. Okay, we have just symbols, but some special symbols like numerical symbols we can define, or we can have the information about the quantity. So first level is the symbol. Second level of the information is the quantity. Yeah, when we want to measure something. The third level is the quantity with means. And the fourth level of the information is the evolution of the information. And the evolution of information, or we can track the information, we can store information, we can make some statistic with some evaluation, and to see that, okay, we have the temperature during a year. Yeah. And in this case, we can say, okay, in this year we had this shape, let's say, or the profile, and the next year we will have something this and this, and we can collect statistics and say, okay, next year we will have something like this on this date. Yeah, and we can use this evolution of information to statistics for some prediction and so on. But we should understand first of all that yes, that the information is data that has means, and when the proper information is propagating in the time we have signal. Yeah. So this is the story about the fourth level of the information. So please provide me some feedback from 0 to 10. Let's say that if you understood the idea of the level of information, what information is, and why we are okay, why is we'll see further, but the principle that I explained it here. So we have some symbols, special symbols. We will use a collection of symbols to codify everything, let's say X, Y, A, B, C. Using some special symbols, numerical, we can define a quantity, giving a meaning for the quantity, let's say the physical meaning of the quantity. We can then define the information. So information is data with means. More than it, we can define the evolution of the information time. We can say that this is a signal. So do you have any signals about something? It doesn't mean that just you see and you have a picture. Yes, a picture will have just information, but video already is a signal because you see in the time how it is the evolution of the information. Okay, thank you for who is participating to our chat, let's say like this, because I need to see what is the level of your understanding and if you are with me, more or less. Okay, then let's continue then to the next slide, and we'll see. Okay, we have this evolution. Yes, we have this evolution, and usually in your laboratory works, usually to gather the information from physical environment in the, let's say, on the processing unit, we will have a special interface. Let's say sensor value is equal to analog grid. Yeah, we'll have an interface that is gathering the information to have it inside of our system. Yeah, and most probably the if we'll want to display the monitor on a plotting, we'll have something like this. Yeah, so here we have already acquired the information inside of the system and we can use it, but somehow we don't like it. We have some problems with this this picture or this plot. Yeah, what is the problem of this plot? The problem is that I don't know what is that, because I see that something is evolving. Yeah, but first of all, yeah, I have from 0 to 1023, most probably. Why? Because of the ADC that we are reading. Yeah, because we are reading the information with ADC. This is the resolution of the converter, and we have raw data that I don't know what is that, because okay, we don't have here the mean. What is that? I don't know. More than it is some evolution, but I cannot understand the tendency, because most probably in case of the temperature, let's say we are gathering the information about the temperature, most probably it should be like this, but I have a lot of noise because the temperature cannot evolve so fast. It's kind of very inertial. It's a value of the nature of the temperature. Environmental temperature has an inertia, big inertia, and we cannot observe some changes, so fast changes, except it is just somehow we are putting in hot water and cold water, but it's not so fast because we have some microseconds here. Yeah. So this information is not what we are expecting to have, because I want to have on my screen, like here, yeah, 17 degrees. But if I will follow this signal, I will have a kind of running letters, and I will not understand. So what we have to do, we have to condition, or to aduce la condiție, to bring to a condition, or to condition the information in order to have exactly what we want. Yeah, we want something. It is exactly what I'm speaking. I started with on the beginning. You listen to the class. You have 100 students, but you can select somebody and to detect exactly what they are speaking. After that, you can transfer your, let's say, ears to somebody else, and you will understand what somebody else is speaking. But for that, you should somehow configure the system, okay, in order to conditioning the information you gather. So to extract exactly what you want and the right and proven information. How to do that? Okay, this is the today topics. So first of all, here we have the, let's say, application, and we should do something in order to have the exactly physical value here and to print it on the screen. Yeah, and in order to condition, we can condition it in different ways. First of all, we can condition somehow to detect information from the, let's say, we have big changes of something. Let's say we have a window, and window is, the position of the window, let's say, is changing somehow, and we should bring this information of the big window in the angle in our case. How we can detect this angle? And of course, we should somehow convert from the mechanical environment, yeah, for some mechanical engineering principles, to convert the information from the physical environment to the, okay, our technology today are mostly electrical. We somehow, with some mechanical devices converting, we should convert it physical to some voltage, because in our electrical devices we have voltages and we manage voltages. More than it, okay, we are measuring, we are converting it, some changes into a measurable voltage, but this voltage can be small or big, and we should go to an amplifying or multiply by number high, bigger than 1 and between 0 and 1, okay, to rise it or to lower it, attenuate. And so on. But let's start step by step. We convert, adapt it depending of the some, let's say, artifacts of the signal, because we have some raw data, change of the position of the window, and we should do something in order to have, let's say, it in our Arduino programming language, let's say, or an Arduino IDE, how we get it there. Yeah, first of all, we have some mechanical conditioning. We have some electrical engineering conditioning here, yeah, in the hardware domain, and we have some software engineering conditioning. And let's see, today we will discuss not exactly okay, here we have an example or a classical way for the conditioning, and we will see what is, let's say, classical methods that are used usually in embedded systems, yeah, for gathering and conditioning information. More or less is, let's say, an unusual or a classical, let's say, methodology, and a simple. If in case we would need some more complex acquisition, most probably you already have another topic or signal processing cars. Just raise your hand if you have such cars on your curricula. Signal processing. Just raise your hand because I know that yes, but I want confirmation from your side. Okay, thank you. Please stay in touch with me because I want your feedback, and it's very important for me to see that somebody's is after my monitor, my screen. Okay, thank you. Again, mechanical. Okay, how we can multiply or attenuate the changes. Let's say we have here something that is detecting, but here is the window. Yeah, the big change of the window can be converted to a smaller change, or big rotation. Yeah, can be converted to small changes by this ideal mechanical advantage. Most probably, even such construction you already had on the mechanics. I don't know, did you had such cars in the first year? I don't know, but as I remember, it was excluded on your side. Yeah, but maybe in the school you see that changing the bigger change here will have small change here, and vice versa. So we'll have a kind of EMEA or ideal mechanical advantage when we are converting something. Yeah, so this is how we can do, let's say, mechanical operation, and this is those are the formula for every particular system that we can use. Yeah, okay, so let's go further. So in mechanics we do some converting of the or changing or adapting. But let's see what means to have hardware conditioning, because sometimes we want to measure something, and let's say we would like to measure some big voltages. Yeah, let's say we have a sensor that is converting the data and converting it to a higher voltage that can be used by a microcontroller, by an ADC. So we cannot apply, let's say, 20. Let's say I'm measuring the voltages on the AC adapter. Yeah. So I cannot apply this voltage here. I should adapt it or attenuate it in order to have the change between 0 and 5 volts, as only this range is supported by ADC. So I somehow should split it or should attenuate or divide it by a coefficient. And how we can adapt it? Okay, we all have out is equal to V in, and using the proper nominals for values for the resistance, we can choose exactly what we need. Yeah, so it's the same as more or less similar. Yeah. Yes, and in case we have from the sensor bigger value that are supported by ADC, we should attenuate it, but sometimes we have smaller value. Let's say we have thermocouple. And thermocouple, it's kind of two metals that were Konstantin, how you said last time, welded, yeah, welded together, and when we are heating it, we will have some voltage, but this voltage will be in the range of millivolts. Okay, let's say from 1 to 10 millivolts. Okay, it's not enough for the ADC because the range is about one division, 4 millivolts per division, and in this case the maximum will be, minimum will be 0 and the maximum will be 2 or maybe 3 from 1033. And in this case the error of the changes will be about plus minus 50%, and we cannot measure with an ADC that is working in range, okay, with an ADC with 10 bit that is operating from 0 to 5 volts and 10 bits giving us from 0 to 2023. We can measure this range, but we will have from 0 to 3 maximum. And in this case, the error will be about 50%, 30–50%, and we cannot measure very, so in this case, the resolution will low to the 3, not to the 10 bits. Okay, this is 1000. Yeah. So in this case, what we can do? We can electrically amplify it. It's very easy. We'll have an amplifier, yeah, and those two resistors that can be adjust the coefficient of multiplying. So V in, V out is equal to you see the report, how to say, of these two resistors, and we can select the proper resistor. More than it, with those two resistors we can even attenuate, not only amplify. So buy a circuit amplifier and adapt the resistance. So yes, so we now, in case we have bigger voltage at the input, yeah, here, let's say, let me, where is my pointer? Okay, let's say, in case we have at this point, we have conversion from the physical to voltage, and in case we have here higher voltage, we should from 20 to, we should lower it. When we have 2 millivolts, we should raise it. Okay, depend of the range, and this is the adapter. And how we are doing that electrically, because the sensor is converting somehow mechanically, I don't know, is converting everything to the voltage domain, because all our devices, yeah, our let's say state-of-the-art devices are electrical. So we, first of all, we should convert it to electrical. After that, having it inside of our device, we should condition it. We should condition it in order to be in the range of the ADC. So how we do that? Simply amplifying, attenuating it. But we can have some another troubles. We can have some another troubles, and we should protect it against some, let's say, we have some changings from 0 to 5. But sometimes, somehow from here we have an induction of 20 volts. So everything will be multiplied and so on. So here we'll have 20 volts. What will happen? These 20 volts applied to the ADC can burn the burn out the electrical circuit. So what we can do, we should protect it somehow. So we can cut this at a certain level, yeah, just cutting it. And we have special devices, Zener, I think, special diodes that are limiting or cutting the higher voltage so I'm not allowing to go to pass through. Okay, so in this case we will cut the voltage that if it is lower at a certain value or is higher at a certain value, because most probably we will not allow the voltage to be lower than 0. Why? Because it will somehow put on the domain that ADC is not working, because ADC is working from 0 to 5. So cutting everything, yeah, amplifying or attenuating, but after that cutting. Okay, but we will have some primary noise because every, by the way, just quick question. Let's make some quizzes, not quizzes, but to see the feedback. Amplifying. Did you understand the idea? I don't want now you to understand how the electrical circuits are working. But the idea how we gather and why we need to amplify or to attenuate the signal from the 0 to 10, please. I'm waiting for your feedback to see if you are with me and if you're understanding the this why we need to adapt the converted, let's say, from the physical environment to electrical signal, to adapt it to be able to use microcontroller. Otherwise, we will not be able to use microcontroller. Okay, okay, we are not able to use this directly to the microcontroller because first situation, it will not be able to measure small voltages and it will be burned by high voltages. We need to adapt to the domain what we need. Most probably we'll need some shifting, not only amplifying, but we need this stage, yeah, amplifying, attenuate, or saturate. Saturation is the protection, okay? Cut everything, okay, we adapted, but not everything adapted, because we can have, let's say, most probably with me, it's happening every day, yeah? But it's not proper protection like this, but we need protect even against the electrostatic discharge. I have it every half of an hour when I'm getting out. And this is high voltage level of the energy, let's say kilovolts, and we should cut it somehow because it will destroy the electrical circuits. Very important stage of the conditioning. Yeah. So hardware conditioning is adapting to the level of the 0.5 0 to 5 volts more than it, but somehow we will have the raw signal, and depends on the length of the wiring, we'll have something like that. Let's say a wire. Let's say like this. Yeah, we have this wire, but let's imagine I need a radio, and most probably your phone, if you want to put it to play aloud the radio, you will need to insert something here. Yeah, and in this case I will have radio. This way not. So if I want radio, I should add some wiring here. Why? Because the wiring is gathering the electromagnetic fields from the radio station, yeah, and transfer it. But not only, okay, in this case is a good case, or is we need that, but not always we need that. We need that for the radio, but we don't need when we are measuring temperature. But anyway, we will have cables and we will have noises. Even we will gather the radio stations on our cables, and we need somehow to clean up the mess. And the first stage is hardware conditioning, and you will see that it is the difference between the high quality and low quality of the electronics. On the high quality of the electronics, you will have some filtering on the high quality. And low quality, like Arduino now, what that you have, you will never have this stage of filtering information. So on the higher quality, more than it, in the medical equipment, you always will have on the input some filtering to clean up the mess, let's say the radio stations. How we can do that? So first of all, most probably we will need some frequencies to pass. Yeah, and in order to select to some frequencies, yeah, we can just close to put a barrier for low frequencies, because the frequency, the high frequency is passing through a capacitor. Now, having this combination RC filter and having this formula, we can combine it in order to see what will be the frequency that is passing through it and what is going back. Let's say like this, like here. Yeah, let me again pointer option. So this one will let some higher frequency than a certain level that we can detect by this formula. Yeah, and some of the frequency will go back. So let's say like this. What is the situation? We have some floating frequency, and we don't want this frequency to float. We want it to be stable. And in this case, when we have something like this, yeah, we want to exclude this floating component. In this case, this one will go back and this one will pass. So we will have the needed information passing through. But in the second stage, most probably we want to exclude, because most probably we already have this information, but it's not exactly like this, but it's very is full of radio noises, and we want to exclude. So we excluded the floating component, but after that we want to exclude the noise of the radio. In this case, we are passing it through this, but the low frequency, and the high frequency will go to the ground through the capacitor. So capacitor is it's allowing to pass the high frequency between fluid, but according to this formula, what is the frequency that will pass and what is not. After that, from this component or this whole, let's say, for the frequency, we can build different filters. So we can let some frequency to pass. After that, some frequency to let fall down to the ground. So in this case, the high pass filter, yeah, this one will cut the low frequencies and the higher frequency will pass. And the second stage will cut the high frequency. So only the low frequency will pass. Here only the high frequency will pass. And now most probably we are interested only in one band frequency. So we can just connect one after another. One will cut the low frequencies, yeah, go back. So the low frequency will go back. And here we will have the higher frequency will fall down. And we will have only a band. So in this case, connecting in serial those two, we will have this band. Yeah. Just a quick theory of the filters, how we can pass, let's say, only the frequencies of the signal that we need. Very easy. We have the formula, and this is the basic formula. We have here RC filter, So the values, we should select the values in order to manipulate with the signal, not to too much theory. I don't want to go to the theory to say how the resistor is working, how capacitor. Just having some components, pass high frequency, after that low frequencies, and we can build and to select exactly the domain of the frequencies we want. Yeah. More than it, putting it in serial, we can do a band. It's a serial, low and pass. But we can have in parallel, let's say RC and RC, okay, and we can have band reject. I want to select the frequency that I will not pass. And usually, what kind of frequency we would like to reject? Usually, we want to reject frequency that is all around us, okay? Because we can see that in the AC adapter, everywhere, our lighting is a kind of a big antenna that is providing a big component of 50 hertz frequency. And usually this is high power and is influencing everything around us. Yeah, every piece of cable is gathering this noise of 50 hertz, and usually we want to pass to cut it, and we can select those RC from here, yeah, and to adapt it to the 50 hertz, and we can build this parallel, parallel filter, RC filter, and to cut it. Why we need to cut it? Okay, for regular, for our Arduino project is not a problem, but for the medical devices, it's very critical to have more precise information. So once again, we will have, taking in account that the high frequency is passing through the capacitor, we can build by this formula all the component. So this combination, when the frequency is passing through the capacitor, allow us to on high pass filter, so to cut low frequencies, and this one allow us to ground high frequencies to allow only the low pass filter. Yeah, this is like this, and this one connecting in serial will have this one, connecting in parallel will have band. But okay, nothing special. You will see that high quality usually have this basic filtering. Okay, we of course we have we can have more complex filters, and even I cannot build it because we can apply some theory of the filters. But these are the basic measures, protection measures against some features. We'll see why we don't need too much filters in the electrical side, because but in the next steps. But I just quick answer. Do you understand the meaning of the filtering, why we need that, and the basic how we can build simple filters? Please provide me an feedback from 0 to 10. Okay, then meanwhile it is coming, your feedback is coming. Let's go to the next slide, but please answer, always answer. It helps me to understand the level of your understanding. So next, what we got to this point? At this point, we got what? We are converting the physical data to some voltage. This is transducer, let's say. Yeah? It's converting to a measurable data. Okay, we can measure, but not directly, because the ADC is working from 0 to 5 volts. We will need to adapt it or to condition it. We are adapting the voltage, cutting the higher and lower voltages, and we are making some basic filtering in order to extract the let's say, low pass for floating artifact, and the high pass filter, the high pass filter, we are extracting the floating artifacts, and low pass filter are excluding the radio wave influence to the cables. Yeah, so here we'll have something good enough, something like this, let's say. Yeah, okay, we have some artifacts, but these are not critical anymore, because let's say we are conditioning it in order to have some basic adapting or basic hardware conditioning. So until this point, we have some hardware conditioning. And now the last stage, we are converting 0 to 5 to the point of 1, 0. Let's say at this moment, what we have. At this moment, we have from 0 to 1023. Yeah, this point. Now let's go further. We acquired this signal from the 0 in the range of 0, 1023. Yeah, but I can't read that. I understand that something is rising, something is going lower. I have some noises. Are those noises good or bad? I know what is that, because I see something. Yeah, but what I don't have here, I don't have here the mean. I don't understand what is that. I see the level, I see the quantity, let's say, I see the signal that is somehow is, I see the evolution, but I can't understand yet, because I want a display, finally, to have 22 degrees Celsius. Here I can't see that. I can see that, and I need to do something. So, but we have succeed to bring the information to the software level. Now everything is in our hand, and we have to do some special methods. Okay, now let's see something interesting, yeah, because we see the methods that are applying in the hardware. We can apply similar method, and in many of the cases we are even transferring the conditioning from the hardware to the software. This is why it's not crucial to have all the conditioning in the hardware and to have the best signal. We are doing here in this hardware only the basic conditioning, and the methods that we discussed before are, for many of the cases, good enough. Why? Because we are transferring the complexity of the problem to the software. So we can do here also some saturation. We'll see why. We can do some amplifying. How to amplify? Just multiply. Yeah. And here we'll need some circuits. That is, every component costs money. But here, how many cost an operation? Okay, it's a byte or something that usually you are not measuring, and usually is for free, let's say like this, because you are already bought a microcontroller, and now it doesn't matter you are putting the formula or 2 formula or 3 formula. Yeah, it's configurable, and this is why in the modern electronic systems, usually the hardware conditioning is transferred. We have only the basic conditioning on the hardware, and we are transferring all the data processor processing to the software. But let's see some basic that are mandatory for our signal acquisition. For the signal acquisition, by the way, let me check again. Did you understand this part on the hardware conditioning in general? What are the stages and what is the meaning of that? Why we need that from 0 to 10? Please. We need to adapt and to perform the basic filtering and adaptation from 0 to 5, and excluding some floating artifacts and some high frequency usually, and to adapt the voltage. This is the main three things that usually are performed. And you'll see the cost of the, let's say, Arduino models. You'll see that you don't have anything there. And usually, and we'll see that for using the Arduino components, usually this workload usually is transferred to the software. And let's see how. Yeah. So this is Arduino component, as I remember, something like or a potentiometer or a temperature sensor. I don't know exactly, but something. Why? Because I don't have here the mean. Yeah. So conditioning. Let's see how we can do the simplest signal saturation, and we'll see why. Very easy. We have some X here, let's say, yeah, at this moment, this one, or let's say this one, sensor value, and we will extract it from here, yeah. And of course, we can do it manually by if sensor value is higher than maximal, so sensor is equal to maximum. That means in case we'll have some evolution like this or something like this, I can cut it. I can cut it. Why? Okay. This protection from here, from the hardware, was necessary to adapt to not have higher than the ADC support. Yeah. But why we need saturation here inside in the software? Because we have formula, we can store everything. Yes, but let's say we have to multiply 10 by 10. It will be 100. So for 100, we can use 1 byte, 1 storage. But what if we'll have 100 multiplied by 10? We'll have 1000. So we can use 16-bit. So an int 16. But what if I will use 100 multiplied by 100? 100 multiplied by 100. Yeah, we will have 10,000. So what I can use? What kind of value? 16-bit. But what if I will use, let's say, 100 multiplied by 1000? So I'll have 100,000. So that means the result will not fit anymore the will not fit anymore the 16 bits. I will need a bigger variables, more than it. All the signals, in order to not use the bigger variables, to use only the 16 bits, we can keep the calculus in the range of 16 bits. And in this case, let's say we have we want to keep it between this value, but at a certain moment we will have some bigger data that will give us bigger result. That is, it is out of our needs, but it will come. In order to not pass it through the formula, we will cut it from the scratch. Yes, it's not good, but even maximal value is not good for us. But higher than the maximum that we are allowing to our formula, it's even not necessary and not good, and we can limit it. So we are limiting in order to not pass high value, to not have high value multiplying another operation. So saturation, please give me some feedbacks from 0 to 10 about the do you understand why we need some saturation here and how we are doing that? Please. So we want to protect against high values in the formula to keep or to save the memory and to not have overshooting or overloading, because this value will not feed the 16-bit, will have overload or overshoot. So how we can do that? First of all, we can do like this, but I strongly recommend to use some libraries. Why? Because here you can have some mistake. Instead of higher, you can use lower, and you will not observe it, and you will see that it's not working for me, everything is crashing. Okay, we should check. Yes, we should check it and to make some protection, I don't know. But what if you are measuring against the max, comparing against the max, and here we'll put the mean? Why? A copy paste error. And in this case, what we'll have? Another error, and most probably you say, I saturated, but it's not working for me. Why? Yes, and this is why I strongly recommend to use some libraries, because let's say this is a Arduino feature or Arduino library function that you can use. Yeah, it's constrained. It's constraining the sensor value between 10 and 100. I know that sensor is providing between 10 and 150, and I will exclude all the artifacts. Maybe I'll have somewhere some detection of this value, and will let's say raise a hand for an error, raise a flag for an error. But after this saturation, I will not have problems with that. Yeah, and now this is already checked by million and million of the applications, so we can use it safely. So thank you for the feedback and who is participating to gather it. So let's go to the next software conditioning method. So now we are conditioning it, and we cut the upper and lower value that we know that a sensor could provide us. Yeah, in terms of voltage here. Yeah, but sometimes we have some energy spikes. How can we cut? Because by looking to the signal, we see that it's not good, but we even cannot saturate that. Let's say we are cutting here and here. Okay, those one we will cut, but we will not exclude this one and this one and this one. We will not exclude, because everything or all the image is going lower and higher, and in this case we should do something. So how we can do that? It's very easy. We have a salt and pepper and filter or statistic filter. Okay, why statistic? Because it's using the statistic. What is most probable value that should be instead of this spike? Very easy. Yeah, what we have an input buffer that we are pushing on this FIFO buffer. What means FIFO? Last is going back there, after that changing or moving all the data here, and the input, the last will stay here. So first in, first out, we have a buffer of where we are organizing a stream that is going through the buffer. Now we'll have a copy. We'll have a copy by a window. Yeah, we'll build a window somewhere here. Yeah. And step by step, we will shift this window through the signal. Yeah, how? Always the buffer will move, the window will stay, and here we have the window of 5 elements. Yeah. Now gathering it and building a plot through this window will have something like this. But what we'll do next step? So first one is buffering. Second, we will get a copy in order to not destroy the buffer, yeah, to not destroy the stream. Copy. Third step, we will sort it, and we will see sorting it. The minima, this one will go here, and the maxima will go here, and we'll have a sorted buffer and most probably the median value will stay somewhere in the middle, yeah, and we can take it as the output value. So now shifting through the buffer or through the signal, we always will have statistically most probable value of this signal. In this case, if we have only one plot higher, it will be excluded. Okay, in case we'll have more than one or more than three, most probably it will cover the middle, yeah. But in case it is just one spike for one point, it always will stay in the extremity of the. So this is how we can exclude just spikes. Let's say we, I don't know, we have a kind of phone noise or somebody switch it on the lamps, yeah, and we have a big electromagnetic spike. In this case, we can just exclude that and will not have those. So now let's see your level of understanding of median filter or Salton-Piper. Did you understand the idea? Please, from 0 to 10, because you will have to implement it, of course, on your laboratory work. So just keep a stream, take a copy, sort it, take the middle. That's all. So here we'll have analog read, push to the buffer, get a copy, sort it, and you will see that you will have all those libraries except maybe the FIFO buffer, yeah? But you will have those libraries always on. By the way, even the buffer, you can copy it, implement it by a copy of shifted. Yeah. So let's go further. 7.51. Thank you, Pavel. So next one. So what we'll have here, we will exclude the spikes, but after excluding the spikes, we'll have something like this. Yeah. Anyway, we'll have, because the spikes already we excluded in the previous method. Yeah. But now we have something like this, and we will see that having such signal, it is equal to the signal, useful signal, plus the noise. So the useful signal usually is that, yeah, so we have this one plus this one. And taking a look to this noise, we'll see that we have something above, something below, above, and having a sum, the sum of the noise is equal to 0. What we can do? We can do a kind of having a window, making a sum of the values, and then and to have an average. In this case, when we are summing, we'll have a sum of the useful signal, but some of the noise will be excluded because the sum of the noise is 0, and having the average of the value of a window, we'll have an average on this window. After that, having a shifting window, we'll have an average for a part of the signal, but without noise, because sum of the noise always will be 0. So it's very easy to do that. More than it, this filter has the name, okay, so usually the formula is weighted average, or the average, let's say, and usually it has the name the low pass. So you remember we had a low pass here, yeah. The capacitor also is somehow smoothing the value because it's a kind of accumulator, a kind of battery. When it doesn't have energy, it's providing from the capacitor, but when it is has more, it's pulling out. Okay, so we have a kind of smoothing or white noise. Maybe you heard in your radio some white noise, shh, meaning nothing, or Gaussian or average, yeah, or weighted average. So now the simple filter can be an average, but there are some tricky parts because I'm understanding to the most recent value more than the one from the history. In this case, I can say that the first value will have the weight of 50%, the second 25, the third 15, and so on. So I can build in order to have the first value, but okay, it's noisy value, but I will smooth it by the history. Yeah. So in this case, what I can do, I can just make an weighted average of the signal. Yeah. X multiplied by the weight plus x2, so the second value or the history of the value multiplied by its weight and so on. After that, I will just sum the weights, so I'll have this formula. Yeah. Now we will see, but by the average we'll have something like this. Yeah, this will be the signal to the output. Yeah, because we'll have in the output the average on the every point. So we'll move by this window through the signal. Yeah. Or back maybe, because it depends on the direction on how we will proceed this signal. If in case we'll store it, after that we'll filter, it's one way, but we can have a different story. One way will just online in real time will do that. So, but let's see, let's make some observation on the formula. In case n is equal to 1, in this case we'll have a kind of sum of x, y, and divided by n. Yeah. So it's in particular case when all the weights are equal. In this case, we'll have a simple average, just sum and multiply to the number. Yes, but when we want a kind of fine tuning, we can use the weight. Yeah, but even a simple average also will work. What is interesting that together with some guys in our club, we got some. We're measuring the cardiogram, and we got some this kind of signal. And what is interesting, we extracted exactly the cardiogram by applying only this and this filter. So those simple filter are filtering very well, and you can try it by yourself. So now the last things that I want to show you is that, okay, we are conditioning, but we have some conversion here and here. Okay, let me see on. So those we already passed, but we see that we have here from 0 to 1023 to 0.5 volts. Yeah, and here we have from 0 to 5 volts to, let's say, I don't know, from 20 to 100 degrees of Celsius. And we should somehow make a kind of conversion from one domain to another domain to adapt. How we can do that? What is interesting for me, when I started to learn mathematics in the first course, it was strange why I need this formula. Okay, but it is a straight line, forma canonica adrepti. Yeah? Straight line canonic form, something like that. Yes, and we will see that we have one point, the second point, yeah, and we have x and y for the, okay, sorry. We have x2 and y2 for this one, x1 and y1 for this point. And now we can extract that x is equal to what? Y minus y1 multiplied to x2 minus x1 divided to y2 minus y1. So in case we have two fixed points, we can convert it to n1. But what if we don't have a straight line dependency? Let's say we have something like this. What we can do? Just split it in segments, and we'll have two stages. First of all, find where is this, because usually in datasheet you will have tables of x, y, and you can select the proper segment, or this one, or this one, or the next one, and so on. Find the proper signal, apply this formula. But don't worry, you have in the Arduino, let's say, library, the function map, and you can use it because it is exactly implementing the this kind of conversion. So that's all. So finally, we know that we can condition it, okay, mechanically maybe, because adapting some, let's say, for the lifting window adapter, yeah. But having it, we are conditioning it in hardware, converting into the software, after that conditioning in the software, and converting back. So what is interesting here, having the physical parameter in the environment, we are converting it to a variable that will have, let's say, 24.5 degree of Celsius. And we can print that. But first of all, we should go through this stage and to condition it in order to have what we need and how we need, and to exclude all the artifacts. So this is everything about the signal conditioning. Of course, we can have different, okay, the temperature, humidity, and so on, and we can have a kind of sensor service, but this is how we are building an architecture and how we can do that. Of course, we already did that. So, and by the way, in the next lecture, after one, we'll have a practice session. We will discuss about that. So we should build everything, the microcontroller. This is Arduino. This is the eBay sensor driver, and we will speak about the services for the conditioning. Yeah, and we'll see how we'll do that. And of course, we'll have something like this. Yeah, more the need, why we need to have this smooth signal in order to not transfer, let's say, to an actuator, to have a kind of hitting everything because the signal it was not properly gathered. So we will need to condition it to have a smooth ergonomical movements, let's say, of the robotic arm. This is one of the example. So this is everything I wanted to discuss with you today. Just please give me an feedback regarding the understanding and interesting about this lecture, and see you next time. So waiting for your feedbacks.